Hello class, we are starting the chapter on electrochemistry. To be successful at this chapter, you have to have mastered the thermodynamics that we talked about in chapter 18, especially Gibbs free energy. And we're going to use energy to determine whether we have a spontaneous reaction, which we think of as a battery, or a non-spontaneous reaction that we may use electrolysis to create a reaction. So we're going to talk about voltaic or galvanic cells and electrolytic cells. So voltaic or galvanic, we're talking about spontaneous reactions, what you would call a battery, and electrolytic cells is where we apply a current or voltage to cause a reaction to happen. This is an especially important chapter if you are interested in electric cars, electric batteries, if you're interested in corrosion, oxidation reduction reactions. These all have, and so in biology, oxidation reduction reactions come into play here as well. So I hope that you have learned material about thermodynamics and that you see why thermodynamics is so important, because this is really a chapter on application of that thermodynamics. So in this chapter, we are going to only cover the first 5 sections, and so it's a shorter chapter, although it does mean that the turnaround time's shorter. I think the PowerPoints due within less than a week, so we're only covering the first 5 sections. So balance and redox reactions. We first broached this concept in Gen Chem 1, and we did some simple balancing of redox reactions. Here we're going to take it a little step further, and we're going to balance redox reactions in acidic and basic solutions. So a little more complex than what you saw in Gen Chem 1. So the first thing is we have to be able to assign redox number, or oxidation numbers are called oxidation states. And if you have not, or if you've not had this, or it's been a long time, I encourage you to look at chapter 4 in this book, and there's a section on redox reactions, and there's a table. And let me just reference the table so you have that to look for. If you go to chapter 4, table, let me see if I can find it real quickly here. Table 4.5, all right? So refresh your memory about the rules in table 4.5. And the other thing to remember about table 4.5 is the rules are hierarchical, which means fluoride being assigned a -1 oxidation state is more important, or takes precedence over sodium, or group 1 and group 2, group 1 being +1 oxidation state, group 2 being a +2 oxidation state. So fluoride takes precedence, then group 1 and group 2's oxidation states respectively, and then after that it's hydrogen is always +1 unless one of the 2 other rules dominates over it. So if you're looking at this slide and you go, I don't know what's going on in this slide, let me kind of refresh your memory here. So you have to be able to look at the substance, and let me see here. So when you're looking at this, everyone knows this is an ionic compound, that the potassium is a +1 ion, and the polyatomic ions, ClO3 negative, is chlorate, and so we want to be able to assign oxidation numbers for every element in this compound. So right off the bat, we know potassium is a positive one. And let me just say, by convention, when we're talking about oxidation states or oxidation numbers, you put the charge and then the number, all right? So there's a rule that says, yeah, potassium should always have a positive 1 oxidation state. So there it is. So then we look at the chlorate, and we can look at it individually like this, or we can look at it holistically like that. But here's what we know. According to the rules, we have 3 oxygen. Each one has a -2 oxidation state. And chlorine, there's no rule for chlorine except that it's almost always -1 unless it's attached to something that's above it. And oxygen almost always has an oxidation state of -2. So we're going to put an X in for chlorine, and here's what we know. When we add up these oxidation numbers or states, it has to equal the charge on the ion, which is -1. So if we solve for this, we get X minus 6 equals -1, and then we add 6 to both sides to solve for X, and we get X equals +5. So that's how we come up with that number. And again, there's a rule for oxygen. So then this is called a decomposition reaction. Why is it called decomposition? Again, this is a review from Gen Chem 1. When you start with one substance and you end up with 2 substances, it's a decomposition. So here's a rule to remember too. Any element in its standard state, free element in its standard state, has an oxidation number of 0. So that's what, if you look at this, oxygen has gone from a -2 oxidation state to a 0 oxidation state. That means it's lost 2 electrons, right? So if you look at oxygen and it was -2, and then it becomes oxygen, and each oxygen's lost 2 electrons, so it's a total of 4 electrons. So really, it's a loss of 2 electrons there. But when we balance this out, there's a total of 6 oxygen, so we're going to have 6 oxygen here, -12. So that means we have to have 3 of these oxygens, and 3 times -2 is, or 6 times -2, so it's a loss of 12 electrons, or if you want to do it that way, loss of 12 electrons. So let's clean this up. It's 6 O2 negatives, where we get the O2 negative here, and then it becomes 3 diatomic oxygens, that's what we see here on the balance, plus the loss of 12 electrons. So that's an oxidation half reaction, because when you see electrons on the product side, that means electrons have been lost. And so we're seeing oxygen lose oxygen with a -2 oxidation state. And I actually did that wrong, didn't I? -2 oxidation state. All six oxygen atoms are losing -2 electrons, and so 6 times 2, that's where we get the 12 here. All right, and so the other thing we see is then we see that chlorine, if you have a redox reaction, one thing must gain electrons, the other thing must lose electrons. So chlorine goes from a +5 oxidation state to a -1, so that's a gain of 6 electrons. So you'd have chlorine, and it's a +5 oxidation state, and you've got 2 of those, and then it gains a total of 10, gains a total of 12 electrons, 12 electrons, and that becomes 2 chlorines. All right. So each chlorine gains 6 electrons. You have 2 of them. So that matches. This is important, that how many electrons you lose, you also gain that amount. And if it doesn't work out perfectly, then you're going to have to use a multiplier to get that to work. So this is kind of the same stuff. This is what we did back in chapter 4. And you said, I don't remember this, then you're going to have to go back to chapter 4 and read section 4.4. kind of brush up on oxidation reduction reactions. So again, what happens here, these numbers are assigned by the rules in table 4.5. And then when you look at this, you see that some things are losing electrons and some things are gaining electrons. And generally the oxygen will let's see how I want to say that. Oxygen, generally metals are reduced. Well, this one's a little different because of the chlorine and the oxygen. So oxygen's actually losing electrons, and whatever loses electrons generally is a reducing agent. Whatever gains electrons is an oxidizing agent. And chlorine's gaining electrons here, so it's acting as an oxidizing agent. Same thing down here. You can see that carbon's going from a -4 to a +4, so it's lost 8 electrons, and hydrogen's not changing, stays the same, so it's a spectator kind of. Well, we don't think of a spectator ion because it's actually part of the compound. But the oxygen is going from 0 to -2. So in this case, oxygen is gaining electrons, which makes it an oxidizing agent. So in this one, we do see oxygen being an oxidizing agent because it's being reduced, and carbon is a reducing agent because it's being oxidized and releasing electrons. Last one here, this is the simplest one. You can see tin solid by itself goes to tin 2 positive. So there's a loss of 2 electrons for tin. Copper 2 positive gains those 2 electrons. It becomes copper solid, which has an oxidation state of 0. And so that's the simplest of those. So again, if that sounds like a lot of gibberish, then you've got to go back and read section 4.4. Because we're going to advance beyond that in Gen Chem 2. So, balancing and redox reactions. Consider the aqueous reaction of iron 2 ion with the dichromate ion. So here we have iron 2 positive going to iron 3 positive, and we have chromium. And what I would expect here is you're able to determine what the oxidation number or state of chromium is. And the way you would do this is 2 times X, because you have 2 chromium here. We don't have a rule for chromium, so that's why we put an X here. We know that this is going to be 7 times a -2 oxidation state for each oxygen, and that's a rule. And then, unless it's a peroxide or a superoxide, and then that has to equal the charge on the ion, which is 2 negative. So what we have here is 2x minus 14 equals -2. So I add 14 to both sides. And so then I have 2x equals positive 12. And then I divide both sides by 2. And that says that x is a positive 6. All right. So chromium is being reduced. It's going from a positive 6 to a positive 3. And iron is being oxidized. It's going from a positive 2 to a positive 3. So iron's losing an electron. It's being oxidized. Chromium is being reduced. It's going from a positive 6 here for each individual chromium to a positive 3. So it says the reaction takes place in an aqueous solution. So we can add H2O as needed to balance the equation. All right. So this is important. This reaction, you're going to use water to balance the oxygens on both sides of the equation. It says this particular reaction takes place in an acidic solution, so we can add hydrogen ions to also balance the equation. All right, so here's the key. This reaction is different than the ones that we previously looked at. So let's go back. Notice these don't say anything about aqueous systems or acidic or basic systems, especially the bottom one. You can see this is just solid and then aqueous water systems. It's not acidic or basic. Here, we're balancing something where there's oxygen present and there's ions present, and we're going to use a different technique here to balance the equation. So break it down into its two half reactions, okay? So that's important. And if you don't know half reactions, again, that's in section 4.4. But you can't have oxidation without reduction. And so there's an oxidation half reaction and a reduction half reaction. The oxidation half reaction, the substance is losing electrons. So in this case, iron is going to be losing 1 electron here. All right. And then reduction says that these chromiums, each one of these chromiums is going to have to gain 3 electrons, because we said they were positive 6 each, and now they're only positive 3. So these are going to gain 3 electrons each. So that's where we're going with this. But before we do that, what you want to do is just write the half reactions, okay? Just write the half reactions. So if you do that, I'm going to erase this because I'm afraid that it will lead to confusion. So let me erase this one positive here. Oops. Erase. Does that zap it? No, it didn't do anything for it. All right, let me do that. No. All right, let's see if I can get that to work. No. I'm having some difficulties here. Why is that not working? All right. Well, let's just forgo the helium. I'm not sure what I did here. Okay. So let's go on to the next step. So then the next step is, once you've broken down the two half reactions, the next step is to balance what elements you have here. All right. So balance the elements with regard to the elements and not the oxygen or the hydrogen. Okay. So that's pretty easy. So the first one up here, we're not doing anything to it. And the second one, we have 2 chromium here. We need to put a coefficient of 2 in front of the chromium ion. Okay? So again, look at the reaction, break it down into its half reactions. Oxidation half reaction, reduction half reaction. Balance all elements other than hydrogen or oxygen. And so what we're doing here is we're learning a protocol, an algorithm to solve or to balance a redox reaction that has oxygen and either acidic solution or oxygens in basic solution. All right, so here's the first step where students make a mistake, and that is what you do is you look at the number of oxygen on the reactant side, and there's none on the iron, so don't worry about this is done. There's nothing to do here. But here we have 7 oxygen. So to balance this, we put 7 waters on the other side, okay? So if you want to balance oxygen, you add waters to the other side, in this case the product side. So that gives me 7 oxygen on both sides. You say, well, this isn't balanced. You're right, we haven't looked at the hydrogen yet, but all we're doing right now is focused on balancing the oxygen. So that's step 3. Step 1, break it out into its redox, its half reactions. Step 2 is to balance all all elements other than oxygen and hydrogen. Step 3 is we balance the oxygen by adding water to the other side. So step 4 is we have to balance the hydrogens, and because since we added 7 waters to this side, we've added 14 hydrogen to this side. We put 14 hydrogen ions on the other side. So the oxygen's balanced and the hydrogens are balanced. Okay, so make sure by step 4 you have the oxygens, hydrogens, and other elements balanced at that point. Now we balance the charge, like how many electrons was lost by the substance or how many electrons was gained by the substance. So we can see here that iron was 2 positive, went to 3 positive, so it's been oxidized and it lost an electron. So if you see electrons on the product side, that means there's a loss of electrons by that substance. That tells you it's an oxidation half reaction. Down here, what we do is you have a total of 6 positive charge on the product side, 2 times 3 positive. If I add the 14 positive and the 2 negative here, that gives me 12 positive. All right. And I need to have 6 positive because the charges have to equal both sides. So that's what tells me I need to add 6 electrons to the reactant side here to balance out the charge on both sides. And that's something that's also mentioned in chapter 4. Section 4 is that charge has to be balanced. It doesn't have to be 0 on both sides or 1. It has to be balanced on both sides. So for the first reaction up here with iron, they both balance out to be positive 2 on both sides because the positive 3 plus a negative 1 is a positive 2. And then down here, they both balance to positive 6 on both sides. So that's step 5. So that's what you see here. So there's a certain number of steps you have to go through in order to get the answer. But you'll get quick at this. You'll do enough assignment problems that you'll go, oh yeah, this isn't that bad. So the next step is when you add half reactions together, and again, this is something we learned in chapter 4, is the electrons on the reactant side have to cancel out with the electrons on the product side, that when we add the 2 half reactions together, you don't see electrons in the final equation. So in the reduction half reaction, there were 6 electrons gained, but up here with the iron, there's only 1 electron lost. So we have to use a multiplier 6 for the entire oxidation half reactions so that the electrons agree that we have 6 electrons on the product side of the oxidation half reaction, and we have 6 electrons on the reactant side of the reduction half reaction. These must be in agreement, otherwise you cannot add these 2 half reactions together. So because there's 6 on the product side here and 6 on the reactant side here, they cancel each other out, and now we can add the 2 equations together. Okay, so when we do that, that's what this slide is showing. The electrons are gone, they cancel each other out. We transfer what's up here to our reactant side, and then we transfer what's on the product sides here down here. And this should be balanced. All right, so right now you want to check to make sure it's balanced. So it's 2 chromium on both sides, we can see that. There's 6 iron on both sides, we see that. There's 14 hydrogen here, 14 hydrogen here. There's 7 oxygen here, 7 times 1, there's 7 oxygen here. So that looks good. Now I see a lot of times students stop at this point and say, I'm done. Well, no, when you're doing redox, you want to make sure, or any reaction really, you want to make sure these charges all are the same on both sides. So we got 6 times 2 positive, that's 12 positive. We got 14 positive here, and we've got 2 negative here. So if I add that all up, I've got 24 positive on this side. 12 plus 14 is 26, minus the 2 negative on the dichromate here gives me 24 positive. Over here I've got 18 plus 6, 0 for the water, and so 18 plus 6 is 24 positive on this side. And I go, oh, this is the correct balanced equation in an acidic solution. How do I know it's acidic? Because I've got hydrogen ions present in the equation. You don't always get those. Sometimes they cancel out, but usually you will have hydrogen ions present if it's an acidic solution. All right, it says for each hydrogen ion in the final equation, add 1 OH ion to each side of the equation, combining hydrogen and hydroxide ions to produce water. Make any additional cancellations made necessary by the new water molecules. Let's see, do they show that? No. Okay, so what they're saying in section 8 and 9 is, let's see if I can erase this and show you what's going on. Yeah, I like this segment eraser, I think, better. So I'm erasing all of this. We know it's balanced. This equation is balanced in an acidic solution. Okay, acidic solution. So the question is, what would this equation be in a basic solution? So let me see if I can pick out a different color here. So here you have 14 hydrogen ions. And let's say I want this in a basic solution. What I would do is I would add 14 hydroxide ions to this side, which means I have to add 14 hydroxide ions to this side to keep it balanced. Well, these 14 hydroxide ions is going to combine with the 14 hydrogen ions to form 14 waters. Now, you already have 7 waters on the product side, so these 7 waters, you would subtract 7 waters from the product side, and you would subtract 7 waters on the reactant side to keep the chemical yield sign correct. So this is 7 waters. You'd have 7 waters left over here. All right, so this would become 7 water. Let me rewrite this. So my final answer in a basic solution would be 6 iron 2 positive ions plus 7 waters plus a dichromate ion. Yeah, my 7s aren't too great. Forms 6 iron 3 positive ions, 2 chromium 3 positive ions. These waters are gone, and then I would have plus 14 hydroxide ions. All right, so if this is correct, everything should still stay balanced. So I've got, and I want to really focus on the hydrogen. 14 hydrogen here, 14 times 1, 14 hydrogen here. 7 oxygen here, and then 7 oxygen there is 14 oxygen. That's balanced as well. 6 iron on both sides, 2 chromium on both sides. All that bounces. Last thing is look at the charge. 6 times 3 positive is 18 positive, plus 2 times 3 positive here is 6 positive. 18 and 16 is 24 positive, minus 14 negative hydrogen or hydroxide ions. So I've got a positive 10 overall on the product side. On the reactant side, I have 6 times 2 positive, which is 12 positive. All right. And then minus the 2 here gives me 10 positive on this side. So now the equation is balanced in a basic solution. So if it's basic solution, you're going to do what it said on the next slide, which is you add hydroxide ions to both sides until all of the hydrogen ions are consumed, and it forms waters, and then you subtract the number of water molecules so that one side doesn't have any water molecules. I guess that's an easy way to say it. All right. So it's 9 steps if you have to do it in a basic solution. It's only 7 steps if you have to do it in an acidic solution. And so based on these slides, you should be able to balance any oxidation reduction reaction that's an acidic solution or basic solution. So let's look at a problem here. It says permanganate ion, which you've heard of. It's the purple stuff in the lab, potassium permanganate used as an oxidizing agent. Reacts and the iodide ion react in a basic solution. So right off the bat, I see the word basic solution, and that tells me that I'm working with hydroxide ion to produce manganese 4 oxide and molecular iodine. So what they just spoke here, you should be able to write that as an equation like so. Okay. So the next thing you would do is assign oxidation numbers. So what we know for sure is oxygen is -2 according to the rules in table 4.5 on page 147, and you have 4 of them. And we don't know what the manganese is, but we know that when we add this together, it has to equal the charge on that ion, which is a -1. So we get x minus 8. X minus 8 equals -1. We add 8 to both sides, and we find that manganese is a +7. All right, so now we know manganese is a +7. This is manganese 7. This is oxygen, it's -2. We know iodine as an ion, whatever the charge is on the ion, that is its oxidation state or number, so we know that one. Then we come over here, we know that oxygen has to be a -2, and there's 2 of them, so that makes the manganese a +4. So manganese has been reduced from +7 to +4. And what's been oxidized, the iodide ion has now become diatomic or molecular iodine, which has and that's a free atom, free molecule of iodine, which has an oxidation state of 0. So manganese has been reduced, the iodide ion has been oxidized, and so we're ready to break this apart into its two half reactions. Okay. So very easy, break it down into what's being oxidized. Again, -1 here to 0, that's oxidation, it's lost an electron. And reduction is the gaining. This is +7, and now it's +4 over here. So that's a loss of electrons, it's reduction. So the next thing we do is balance all elements other than oxygen and hydrogen, and so that's why we have to put a 2 here, which is what they show here. So the iodine elements are balanced. Manganese, there's one manganese on both sides, so we don't have to worry about that. They're the same on both sides. Okay. So then we're ready to, once we have this balanced here as well, they're the same, we're ready to move on. We want to balance the oxygens. How do we balance the oxygens? By using water. Okay. So there's no oxygen in this one, so we just leave it as is. But here we got 4 oxygen. We only have 2 oxygen here, so that's why they added 2 water, to give me the same number of oxygen on both sides of the chemical yield sign. So when I added the 2 waters here, I have to add 4 hydrogen ions to this side because I have to balance the hydrogen now. So that's what they did here. Okay. And then, so now our hydrogen and oxygen are balanced on both sides. So the next step is how many electrons lost or gained. Well, we can easily see here this was 2 negative on this side. Each iodine lost 1 electron, but we got 2 of them, so total loss here is 2 electrons. That's the oxidation half reaction. Again, if the electrons are on the product side, it's an oxidation reaction. And here we went from, again, a +7 to +4. We know this gained 3 electrons. The manganese gained 3 electrons. So what we would say is the permanganate ion underwent reduction, and the iodide ion underwent oxidation. So these aren't in agreement. This is really important right here. This is -2, 2 electrons lost, and this is 3 electrons gained. What number do both 2 and 3 go into, which is 6. And so that's why we multiplied this entire equation by the iodine equation by 3, the iodide half reaction by 3, and that is why we multiply the permanganate reaction by 2. Make sure you do this correctly. If you write it down, you won't have any problems with this. You've got to write it down on paper. So let's clean it up. So that's what it looks like. The electrons are going to cancel out. They must cancel out always. If they don't, you've made a mistake. Then we translate these 3 reactants down here, and we translate these 3 products down here. And so cursory look at this, we know that all the things are balanced, right? 4 hydrogen, or 8 hydrogen, 8 hydrogen, 2 manganese, 8 oxygen, 2 times 2, 4 oxygen, and 4 times 1, 4 oxygen, 8 oxygen, and 6 iodine atoms on both sides, or moles, whichever way you want to think of it. So this is balanced. One last thing I always think you should check, and I can't stress it enough, is make sure the charge is balanced. So 8 positive and 2 negative and 6 negative, the overall charge on this side is 0, and the overall charge on this side is 0. So it's balanced. It just happens to both of these are 0 instead of +3 or +6 or whatever like that. So charge is balanced. So then I have students say, I'm done. I've done enough work here. I'm finished. But remember, it said basic solution. So this could be one of your multiple choice answers. That's telling me you're not reading the question carefully enough, that this said in a basic solution. So to make this a basic solution, you have to add 8 hydroxide ions to the reactant side, and to keep this correct, there has to be 8 hydroxide ions added to this side. So these 8 hydrogen ions and 8 hydroxide ions are going to make 8 waters. And you have 4 waters already on the product side, so you're going to subtract 4 waters from both sides. Got to subtract 4 waters from both sides. That cancels those out. You get 4 waters left over here. So 4 waters should be included on the product side. So let's combine that together to see our final equation. I like these problems. They're kind of like a puzzle. Here they're showing you adding the 8 hydroxide to both sides like we just did. It forms 8 waters here, and there's 4 waters here, and then we got to subtract off 4 waters from both sides of the chemical yield sign. And then our final equation is going to look like that. All right. You know this is in a basic solution. You see the hydroxide on here. You don't see any hydrogen on. So this is the balanced redox reaction in a basic solution. And you can check to see that all the elements balance out and the charges balance out. I mean, it's really easy on the charge, right? This is 2 times -1 plus 6 negative. It's 8 negative on this side, and it's 8 negative on this side. It's balanced, all right? So that's what I'm expecting you to do on both the assignment and the quiz and the exam, is to be able to balance a reaction either for acidic solutions or basic solutions. All right. Let's stop here and then we'll pick up on galvanic cells. So this is the first lecture. It's really important. You have to be able to balance a redox reaction, both in acidic solution, basic solution. If this seems difficult, I think it's because you need to go back and refresh your memory and read section 4.4, and especially know your oxidation rules in table 4.5. I hope that helps. Thank you.